Welcome to the video lecture over Chapter 7, or at least portions of Chapter 7. Shown here is the Chapter 7 overview, and so we will cover most of this material. We will definitely learn how to describe mathematically electric and magnetic fields of transverse electromagnetic waves. We'll learn how to understand polarization properties of EM waves. We will definitely learn how to relate the propagation parameters of a wave to the parameters of the material. We'll learn how to characterize the flow of current in a conductor and use it to calculate the resistance of a coaxial cable. And finally, we will also understand a little bit about the power in electromagnetic waves. So the table of contents are listed over here. We will actually not discuss RFID systems, nor will we discuss liquid crystal displays in any depth. So we use traveling waves widely in the world and in our society. Primarily, the way situations work is we have some sort of transmitter, which can be your cell phone, it can be a broadcast tower, can be any number of things that transmit energy. As a general rule, waves do not propagate the ionosphere, and so basically traveling waves tend to bounce back and forth between the transmitter and the ionosphere and the Earth's surface until they reach some kind of receiver. So as a general rule, these waves can be unguided or they can be guided. In a little bit of a sense when we have, let me go back, a little bit of a sense when we have a transmitter and waves are bouncing off the ionosphere, to some extent they're bounded there as well because they're bounded between the Earth and the upper atmosphere. It's a little easier to visualize guided electromagnetic waves in something like a coaxial cable where we have an inner conductor and an outer conductor that's often grounded, and the electromagnetic wave is traveling inside the conductor. In a circuit's perspective, we assume that the wavelength of the wave is sufficiently long such that the current and voltage changes simultaneously everywhere. In a field's perspective, the wavelength of the wave is on the order of magnitude of the structures in the circuit, and so we now have to go to a traveling wave model as opposed to a circuits model, lumped parameter model. So the other way that we think about waves are unbounded electromagnetic waves, and this would just be where you have some sort of radiating antenna, and when a wave is unbounded, it always initially begins with a localized charge distribution that's changing in time, that's creating the wave, or a current dipole that changes in time and creates the wave. And if you get a little bit away from that, everything looks like a point source, and so your wavefront is a spherical wavefront. Now, if you get really, really far away from that, as far as the observer is concerned, by the time you're far enough away, if your receiving antenna or your whatever it is that's receiving the energy is small enough, then the wavefront for all practical purposes looks like it is coming in. Basically, if this is the direction of travel, the electric and magnetic fields look like they're perpendicular to that. So it looks like a plane wave or a wave that has a flat wavefront. And so we approximate these spherical waves as plane waves because typically by the time you get a reasonable distance away from the source, the aperture of the observer is so small that for all practical purposes you don't see the spherical shape of the wavefront. So for the remainder of this chapter, or at least for most of this chapter, we're going to be talking about what's referred to as a uniform plane wave. In a uniform plane wave, the direction of propagation is perpendicular to the electric field, which is perpendicular to the magnetic field. All right, so let's look at this from the perspective of Maxwell's equations. So here are Maxwell's equations summarized here. And what's been done here is we've already made the assumption, if you recall, the curl of E was equal to minus the partial of B with respect to T. So we've already made the assumption that the electromagnetic field is varying with a sinusoidal frequency of omega, a single sinusoidal frequency. So a phasor transformation has already been done in the time domain to take the time domain to a phasor domain. So in this form of Maxwell's equations that you see in this top left gray box, the time variation has been removed by substituting the phasor form. So that's where this minus j omega comes from. So likewise, the curl of H equation contains a current density component, which is your conduction current, and then it did contain partial of D with respect to T, which was your displacement current. Epsilon E was substituted for D, and then J omega was the phasor transformation of that derivative with respect to time. So I want to look at this curl of H equation in just a little bit more detail. So when we take the curl of H, we get the conduction part and the displacement part. But remember, the conduction current is equal to sigma E. So if we substitute sigma E for J, then we get this sigma plus J omega epsilon in parentheses multiplying the phasor electric field. So we can factor out a J omega, and if we do that, then the term inside the brackets mathematically becomes epsilon minus J sigma over omega. The minus sign comes about because basically we divided sigma by J omega, and then we multiplied by J over J, creating a negative sign and bringing the J to the numerator. Now this term here is referred to as the complex permittivity E subscript C, and so we will substitute in this curl of H equation, we will basically substitute sigma E for J, and then we will use the complex permittivity substituted for this term in parentheses, so that we get an equation curl of H is J omega epsilon C, complex permittivity, times E. And so you just need to remember that this epsilon C in general is a complex number. Now you'll note that if sigma goes to 0, the conductivity goes to 0, and we have a perfect dielectric, then the complex permittivity becomes a real number. Now as you recall, for any vector field, the divergence of the curl is equal to 0. Maybe you don't recall that, so I'll remind you. For any vector field, the divergence of the curl is equal to 0. And so because E is equal to the curl of H, then the divergence of E is equal to 0, and hence any volume charge is equal to 0. So Maxwell's equations then become what we see in this gray box on the lower right-hand corner. And these are the equations that we're going to use to work with in order to derive what we refer to as the wave equation for electromagnetic waves. So once again, what are the assumptions that we've made so far? So far, we have made the assumption that we have a linear isotropic homogeneous material, which allowed us to make the substitution of mu H for B. We've made the assumption that, and also of epsilon E for D. And then we've made the assumption that, that the electric and magnetic field are sinusoidally varying single frequency fields. Okay, and a little bit more about the complex permittivity. Sometimes you'll see this referred to as epsilon prime minus J epsilon double prime, where epsilon prime is equal to epsilon and epsilon double prime is equal to sigma over omega. Now for a lossless medium, which has a conductivity equal to 0, this epsilon double prime is equal to 0, and the complex permittivity becomes real as we stated in the last slide. So now it's time to derive what's referred to as the wave equation, and we do that by making a series of mathematical substitutions. So we're going to work here with the curl. We're going to look at the fact that the curl of E and the curl of H relate E and H to one another. So basically, if we look at this set of equations, the curl of E is J omega mu times the curl of H. So what did we do there? We took this equation, 7.6b, and we took the curl of both sides. So that's what's done in this operation right here. And then minus J omega u is a constant, so it comes out. So this curl operation was performed on both sides of equation 7.6b. Now, once we do that, we can see that here you have this curl of H term, but that's already defined as j omega epsilon CE. So we're going to substitute j omega epsilon CE in for the curl of H. And so that's what's done in this line. So here's that j omega epsilon CE, which is equal to the curl of H in this term in equation 7.9. And so when we do that, we're going to get a j squared, which will cancel out this negative sign, and then we'll get an omega squared mu epsilon. So the curl of E is omega squared mu epsilon CE. So there is an expression for the curl of the curl. And the curl of the curl from vector calculus is equal to the gradient of the divergence of E minus the Laplacian of E. So that comes once again from Fields 1 from vector calculus. So if you don't remember that, that should be in that set of equations that you have from the first set of slides that was distributed. That was a review of Fields 1. Now, del squared of E, by definition, is the Laplacian of E. And so if E is some field, then the Laplacian is given in rectangular coordinates by what's shown between these brackets here, the second partial with respect to x squared plus second partial with respect to y squared plus second partial with respect to z squared. So basically that is what the Laplacian is. Now, given the fact that the divergence of E is 0, from this form right here, we can make this term equal to 0. And so what we're left with, if we look at this equation, is we will have this on the left-hand side with this gradient of the divergence equal to 0, and we'll have omega squared mu epsilon CE on the right-hand side. So the left-hand side becomes minus del squared E, and the right-hand side becomes omega mu epsilon CE. So when we combine those two terms on the same side of the equation, we get equation 7.13 here, which says that the Laplacian of E plus omega squared mu epsilon CE is equal to 0. Now this is known as the homogeneous wave equation for the electric field E. And we can define what's referred to as a propagation constant, gamma squared, to be this constant minus omega squared mu epsilon C. So that allows us then to rewrite the wave equation as is shown here in 7.15. So del squared of E minus gamma squared E is equal to 0. Now we actually could have done exactly the same operation that we did on equation 7.6b to equation 7.6d. In that case, we would have come up with an equation in H only, and that would then yield the wave equation given in 7.16. So the wave equation is basically the same equation, and gamma is the same constant for both E and H. So equations 715 and 716 give us the wave equations for the electric and magnetic fields respectively.